This video is about simplifying radicals. Simplifying radicals is an extension topic for 8th grade. It is required for anyone going to Accelerated, but is a skill that all students are going to need next year, so whether you learn it now or then, it will be useful. We're going to first look at a fraction. 8/6, which we know we could simplify to 4/3, or 1 1/3, is still simplified and is still exact, versus if we estimated this to the nearest tenth or rounded it to the nearest tenth, we would say 1.3. This value right here is close to 8/6, but it's not actually exactly the same or equivalent to 8/6. And that is because if we were to write the equivalent decimal, it would be 1.3 repeating, and there would be an infinite number of threes there. We see the same idea with radicals. So far, we've done a few things with radicals. One is we have determined the consecutive integers a radical falls between. So for example, the square root of 18 falls between 4 and 5, and my work for that usually would look something like this. Square root of 16 and square root of 25, which are perfect square radicands or rational square roots that I know. And so a good approximation for square root of 18 is about 4.2. Now, if I were to square 4.2, I would not get exactly 18. Versus today, we're going to simplify radicals. And so I will do a lot of examples, but essentially what that means is that the square root of 18 is actually the square root of 9 times 2, or the square root of 9 times the square root of 2. We can move interchangeably between these, and I often won't even write this step. And we can simplify part of that. So we know the square root of 9 is 3. So therefore, the square root of 18 simplifies to 3 root 2. That's the general idea of what we're doing. You might say, well, why do we care? And this is going to allow us to do a lot of operations like addition and subtraction with radicals, and it will end up being better for some things. Now, similar to with fractions, where sometimes you want a mixed number and sometimes you want an improper fraction, depending on the situation. Sometimes this will be more useful and sometimes this will be more useful, but simplifying radicals is something that you'll spend a lot of time doing in Algebra 2. And so I'll show you some different examples and some different strategies to get there today. Now notice if you wanted to check this, we already talked about how I could do 4.2 times 4.2 to see if I get 18 or close to it. And here I would say, well, what is the square root of 18 squared? Well, that's just 18. And what is 3 root 2 squared? Well, I would have to square the 3 and square the root 2, just like we saw in the exponent unit. So I'd have 9 times 2, which is also 18. So I could check that those are equivalent. So let's open up our notebook. This year it is on page 145, but if you are in a future year watching this video, it might be on a different page. And I'll let you kind of read this top, but essentially simplifying radicals keeps our answers exact rather than approximations. So far in this unit, you have seen simplifying when our radicand is a perfect square. So this whole section right here should take you, a very short amount of time to fill these in. This would be 2 times 15. So this is 30, 4, negative 11, negative 2, and 2. And then you've also seen if we have a negative radicand, and I'm going to skip the rational or irrational part, but everything above is a rational number because our radicands were perfect nth roots. So in a square root, it was a perfect square. In a cube root, it was a perfect cube. We have seen that we get a non-real or imaginary answer when we have a negative inside of a square root. And that when we have a negative inside of a cube root, we actually can take the cube root of that. As a little side note here, if I were to simplify the square root of negative 1, we would write that as 2i, I for imaginary. And the square root of negative 9 is 3i, I for imaginary. And you'll see some harder ones in the challenge packet where you are simplifying and have an imaginary. But again, that is sort of a separate topic. Now, we've seen a few problems that are similar to this section here, where it kind of comes naturally. I'll jump all the way down to E, where the square root of 179 times 179 is 179. Since we have the same factor in here twice, we know that we're taking the square root of 179 squared, and we could cancel out those squared and square roots. And this idea is going to come into play when we are simplifying these larger radicands that are not perfect squares. I could do that multiplication out, but there's no reason that I'd want to, because then I just have more work for myself. Similarly, with a problem like G, instead of multiplying 2 times 2 times 3 times 3, which I could do, I can say, well, I'm going to be taking the square root of 2 squared and the square root of 3 squared. There's nothing left in my radicand, so my entire answer here is 6. And if you did do that multiplication, you would see that this problem was the square root of 36. So now let's really get into it. Let's simplify square roots and some cube roots eventually, where our radicand is not a perfect square. So the most efficient way to do this is to have your list next to you or have those perfect squares memorized and think about how we could break our radicand into the largest perfect square factor and all remaining factors. So my factors of 18 I could list to the side. We'd have 1 with 18, we'd have 2 with 9, we'd have 3 with 6, and the largest perfect square factor there is 9. I also could have my list, and I could be moving down my list and see all of my perfect squares, 1, 4, 9, 16, etc., and see which of them is a factor of 18 and pick the largest one, which again would be 9. So the square root of 18 is the square root of 9 times 2, or the square root of 9 times the square root of 2. I think this is the same example we already saw, but that's okay. So this simplifies to 3 root 2. This is my final answer here. Some other strategies that you wouldn't necessarily need with a problem this small, but I will show you, would be to make a factor tree. So I could split this into 9 and 2, 3 and 3. My prime factors then are 3, 3, and 2. So my square root is the square root of 3 times 2. And then use the strategy that we saw here to take out anything that we have perfect squares of. So I see that there's a 3 squared inside, so I'll have a 3 on the outside. What's left inside is 2. So I'd again get 3 root 2. Some people even do it directly from the tree. They cross off their 3's, write a 3 on the outside, see what's left, multiply those together to be on the inside. All right, square root of 24. So I could think of all of my perfect square factors. The largest one that goes into 24 is 4. 24 is 4 times 6. And I know the square root of 4 is 2. So I end up with 2 root 6 here. Again, had I decided to break this up and write all of the prime factors, I would have had 2 times 2 times 2 times 3. That's 24. 2 squared means I'll pull out a 2, and I'm left with 2 times 3 inside, which is 6. Sometimes we might accidentally, along the way, either not pull out the largest perfect square factor or pull out a different factor. Like maybe you took 24 and you decided to write that as the square root of 8 times the square root of 3. Not a big deal, right? 8 is 4 times 2. And so we would still get 2 root 3, put those back together. But this is the most efficient method. This is the most efficient method. This tree is a great fallback, especially if you have a really big radicand. 75. So I love when there is a multiple of 25 because I can usually recognize it right away. So the square root of 75 is the square root of 25 times the square root of 3. So it is 5 root 3. Square root of 200. All right, so 200. 100 is a perfect square factor of that. Love that. Times root 2. So 10 root 2. Right here. And let me just sort of go back to what I said about checking. So a common error that I see instead of writing 10 root 2 is that people write 2 root 10. So let's think about, well, if we were to put this 10 back in the square root, 10 is the square root of 100. And so I can see that this is the square root of 100 times 2, which is correct. Versus if I had put 2 back in a radicand, 2 is the square root of 4. And so I would have had the square root of 4 times 10, which is not what we wanted there. Also, to another point that I made earlier, let's say you took the square root of 200 and for some reason you decide to break that into the square root of 25 times the square root of 1, 2, 3, 4, 5, 6, 7, 8, and got 5 root 8. Well, that is equivalent, and when you square it or check it or whatever, you would get something correct. But we see that 8 is still here, and 8 has a perfect square factor. 8 is 4 times 2. So we'd get 5 times 2, root 2. Not a big deal if you do this. It's sort of like when you're simplifying a large fraction, and instead of dividing by the best thing to simplify by, you like divide by 2 and divide by 2, and then divide by 2 and divide by 2 again. You'll still get to the right answer. 17, we have 7 times the square root of 48. So 7 is just a coefficient there, and I still need to break the square root of 48. You may or may not know that 16 goes into 48. That will be the most efficient way to do this. So I'd get 7 times 4, root 3. So 28 root 3 here because we already had a coefficient on the outside. This is definitely one that sometimes people end up using a different method. Maybe you break the 48 into 4 and 12 and you realize, oh, I'm not done, got to keep going. Or maybe you make a factor tree there for 48 and use a different strategy. Let's jump down. We'll go all the way down to the cube root here, cube root of 24. So same idea, except I'm looking for the largest perfect cube factor of 24. So my cubes, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. I'm already getting too big here. So I know the biggest perfect cubed factor of 24 is 8. This is 8 times 3. The cube root of 8 times the cube root of 3. I end up with 2 times the cube root of 3 as my answer here. We really focus on square roots, but you should be able to apply this to any nth root. If I were writing out all of my factors, maybe I made a factor tree, and I know that 24 is 2 times 2 times 2 times 3. I think we saw that earlier. Now I'm looking for where I have 3 of the same factor. I have a 2 cubed in here, 3 factors of 2. That tells me I'll write a 2 as a coefficient. What's left inside is this cube root of 3. And then we'll just jump down to this next section. Sometimes you have a radicand that is already simplified. So I know that this is already simplified because my only factors of 10 are 2 and 5. I don't have the same factor twice. These factors are relatively prime. And so I know that I'm already simplified. You could either write the word simplified or you could just write the square root of 10. So we see that across this entire row here. They are still irrational roots. We would have to estimate them if we wanted to place them on a number line. So what I would say is go ahead and you are welcome to try some practice here in the notebook, or you can jump right to the practice in your packet.